Hello guys, welcome to my channel Knowledge Unlimited. As per the audience request, I'm planning to continue few examples on static timing analysis, and I found this example pretty much interesting. So if you see here, there are two flip-flops given of setup time 3 nanoseconds, hold time 6 nanoseconds, and the propagation delay of the flop is 2 nanoseconds, and it's same for both flip-flop 1 and flip-flop 2. So what makes it more interesting is there is a feedback path here, if you can see. So from the output of flop 2, it is again coming as input to this NAND gate and it's going here. Okay, so the combo logic here, entire delay you can treat as 1 plus 1 plus 1 plus 2, that is 5 nanoseconds. Here the combo logic delay, and here also there are two 1 nanosecond inverters placed in the clock path. So the clock path delay here is 2 nanoseconds, and here the clock is going without any delay to the flop 1 with a delay of 2 nanoseconds to flop 2. So this is the circuit explanation. So the question that was asked is to calculate the maximum frequency of operation, and then if there are any hold violations in this circuit or not, you need to figure out, like, if there are any hold. Also we will see how to rectify the hold violations as well. So without any further delay, let's start. So I'm going to just draw a clock pulse here, or a clock signal. So this is one clock signal. Let's say this is at the flip-flop 1. So now for the flip-flop 2, the same clock signal with a delay of 2 nanoseconds we can draw, right? Because there are two inverters that were placed, and this delay will be 2 nanoseconds. This is at flip-flop 2. So the same clock I'm drawing with a delay of 2 nanoseconds. And it was given like the setup time, the hold time, the propagation delay. Now, what is the maximum frequency of operations? So that is the first thing that was asked. So let me change the color back to blue. Okay, so in general, if you recollect the setup time or hold time equations that we have talked in the previous tutorials, if not, please go and watch them. So the clock period will fully depend on the setup time calculation. So how you will calculate the setup time here, or the maximum clock frequency here, is you will have some propagation delay and some combo logic delay, and setup time is like before the clock edge, how much time ahead of the clock edge the data should become stable, that is called as setup time. So there will be setup time of flip-flop 2 here, T setup time. So your clock period should be greater than summation of all these delays. So here your clock period indirectly at flip-flop 2 is having this much window from this edge to here. So it's like the clock period plus 2 nanoseconds. And how much it should accommodate, or it can accommodate, is the propagation delay of flop 1 plus the combo logic delay plus the setup time of flip-flop 2. So this is your entire max delay that you can accommodate in this cycle here, So what now you can do is, this entire cycle delay is this, which is equal to t clock plus 2 nanoseconds. So t clock plus 2 nanoseconds should be always greater than or equal to t propagation delay plus t combo logic delay plus t setup time of flip-flop 2. So if you see now, the maximum clock period, or its minimum actually, the minimum clock period should be, propagation delay is given as 2 nanoseconds, combo logic delay we calculated as 5 nanoseconds, and the setup time of flip-flop 2 is given as 3 nanoseconds. I'll change the color for better visualization. So here now you can simply, you can simply cancel this 2 and 2 nanoseconds. So t clock should be greater than or equal to 5 plus 3, 8 nanoseconds. So this is the minimum clock period that is needed. If you see, right, with this minimum clock period only, you can accommodate all this logic into it. So the maximum clock frequency of operation should be 1 by t min, which equal to 1 by 8 nanoseconds. The same thing I can write as 1000 by 8 into 10 power 6, because nano is 10 power minus 9 if it goes up. I think this basic calculation you all aware. So 4 2s are 8, 4 25 is 100, 250. So it will be 125 megahertz. So the maximum frequency of operation here is 125 megahertz. So that's simple. So now let's see if there are any hold violations in this example. So if you see clearly here, for hold violation, we already talked about hold violation. If you are not aware of it, please go and watch the hold violation tutorial. So it's like here the delay is 2 nanoseconds and the net delay is not given, so let's take it as 0, and the propagation delay of flop 2 is 2 nanoseconds. So hold delay is calculated usually at the same clock edge. So if you recollect from here how much time it will take to reach within the same cycle window. So now your hold time should be sufficiently enough so that your entire combinational logic delay should be greater than that. That much time at least. The amount of time that you'll hold, your combo logic delay should make that signal to at least delay by that time. So from that, your hold is given as 6 nanoseconds, but your combo logic delay is 2 nanoseconds of propagation delay plus 2 nanoseconds of NAND gate delay, which is 4 nanoseconds, and this delay is less than 6 nanoseconds. So clearly your data, the fresh data to that same clock edge will come very much early than the previous data that is being processed. So clearly there is a hold violation at this point. So to overcome this hold violation, you can just place two inverters of 1 nanosecond each delay so that you'll add up plus 2 nanoseconds to it, and you exactly meet the hold violation thing to overcome that. So I hope you guys learned something new in this video. Stay tuned to my channel. I'll come with new examples soon.